Hello, it's Mr. Tuxford here. This video is just going through a practice exam that I wrote. If you haven't done this one yet, please do it before you watch this video. I'll just scroll down, you can pause it, screenshot the questions, and then answer them before you watch the video. Feel free to skip ahead about 30 seconds if you have already done it. Alright, those are all the questions. So 3 questions with about 4 or 5 sub-questions each. And as we go through this, we'll be also talking about the key physics behind each question. So do watch this video if you need extra help. If you were confident in this exam and the mark scheme made sense to you, honestly, don't watch this video. This is for those that want some extra support. Alright, so question 1, a drone crane. Wonderful. So it's going to go up and down. It's 20 kgs, but it lifts 30 kgs. So what would its total mass be? Well, its combined mass would be 50 kgs. So be on the lookout for if mass is separate or if it's combined. And it lifts a 30 kg crate to the top of a 20 meter tall building. So that's a height, h. In 2 minutes. Awesome. So minutes, thinking time, so T for time. However, are minutes SI units? Are they the standard units? No, it should be seconds. So 2 minutes would be 120 seconds. So part A, by first showing that the potential energy is 10,000 joules, calculate the power output. So 2 parts. We need to calculate potential energy, and we know it's going to be 10,000, but we do need to show the steps. And then using that, we need to calculate the power output. Alright, so potential energy. Let's just do, trying to scroll to the side. Let's just do a quick side note on potential energy. So looking in the formula sheet, right at the top are the equations for mechanics. And the second one, EP, is our gravitational potential energy equation. So EP, oh, please hold. Come on, there we go. EP equals mgh. So what does EP stand for? Well, that's gravitational potential energy. The mass is m. G is gravity, which on Earth we take as 10 newtons per kilogram. Right? If we go to a different planet, that constant can change. So do read the question. And if it doesn't say it's on another planet, it's safe to assume it's 10 and we're on Earth. And h is the height, and it's not always the height above the ground. It can be the height above some other thing. For example, like a table, right? You lift your book off the table, it has potential relative to the table. Of course, if you dropped it on the ground, it has potential relative to the ground, so the heights can change. Alright, so that is gravitational potential energy. So now let's use that to answer the question. So start by writing out the equation you'll use. EP equals mgh. New line, still looking for EP, so that comes down. Mass, we know the mass of the drone and the crate is 50. G, assuming it's on Earth, which is, a safe assumption most of the time, G is 10. And in case you forget, it is given in this formula sheet. And what is H? H is not necessarily the maximum height, but it's the height relative to where it started. So in this case, we're assuming it starts on the ground, so we're using the full 20 meters. So 50 times 10 is 500, 500 times 20 is indeed 10,000. Cool, and joules are the unit for energy. So if you got here and your answer wasn't 10,000, for example, if you just use the 20 kg from the drone, you'll know something's up and you can revisit the question and hopefully realize your mistake. Okay, what's next? Calculate the power output of the drone. Okay, so let's have a look at our formula sheet again. What equation relates power and energy? So the top row is a good place to start. It's mechanics. We've got kinetic energy, potential energy, gravity, work. Okay, no. Second row is thermal energy. Not relevant at the moment. Last row is mostly electrical energy, but the last equation, E equals PT, relates to all energy types. Cool, and that's the one we'll be using because P stands for power. So E equals PT, and the triangles there, the delta symbol just stands for change in. So change in energy equals power times change in time. And if we're solving for power, we want power, so we will divide T across. So power would be energy per time. And so power is how much energy you can output in how long it takes. So if you output the same energy in a shorter time, you have a higher power output. Right, whereas if it takes you longer, your power output is lower. So now that we have the equation we're going to use, we can substitute in energy. In this case, it was 10,000 joules. And what is the time? What is the time it took to gain that potential energy, which in the question it said 2 minutes, and we quickly called it out as not being SI units, so that's 120 seconds. And if you compute that, it should be 83.3 watts. Watts are the unit for power. Cool. Alright, and that is a merit question. If you only got one calculation correct, that would be achieved. Alright, question B. At the top of its lift, so it's reached its maximum height, and now it is moving horizontally. Let's just say it's going to the right at some constant speed. Explain why no work is being done on the crate. So, going back to your formula sheet, we know work in the top right is force times distance. Okay, so what's the force acting on the crate in the horizontal direction? That's a tricky one. So it is being held by the drone, but in fact there is no horizontal force acting on the crate because it's traveling, well, there's no net force, definitely, because it's traveling at a constant speed, right? It's not accelerating. But let's actually consider the other definition of work. You may have come across this. Work is energy transferred. So what that means is if you, for example, start pushing something and you give it kinetic energy, you have done work on that thing. If you lift something up, you have given it potential energy, so you have done work on that thing. in this case, the crate is at the same height, right? It travels horizontally. So if it's at the same height, is it gaining or losing potential energy? It's not. So we can say crate at same height or same h, so no change in potential energy. Right, it's not gaining or losing potential energy. Okay, but does it have potential energy? Yeah, it does. Right, it's 20 meters above the ground and it's got a mass, but it's not gaining or losing potential energy. Okay, that's just one perspective. What about kinetic energy? Is it moving? Sure is. Does it have kinetic energy? Yep. Is it gaining or losing kinetic energy? Have a think. If it's at constant speed, is it gaining or losing kinetic energy? It's neither, right? It's at a constant speed, so its kinetic energy is constant. So we can write crate at constant speed, so no change in kinetic energy. Yeah. And so what does this mean in terms of work being done on the crate? Well, there's no change in potential or kinetic energy, so we can say hence no work is being done on the crate. Full stop. And that is a merit question. So key takeaway from this one: work, energy transferred, so that is a basic definition of work. And what does that mean? Well, in this context, we're not transferring any energy into the crate. Right? Its height stays the same, so no change in potential. Its speed stays the same, so no change in kinetic. Hence, no work is being done. If you have a look at the mark scheme, the other way of explaining it is work is force times distance. Since the force acting on the crate is in the horizontal direction, excuse me, let me start that again. Since the force acting on the crate is in the vertical direction, right, it's being held up by the drone, otherwise it would fall down. Hope that makes sense, right? The crate sees the drone pulling it up. So there's a force acting on the crate going up to oppose its weight force, so that it doesn't fall. And so that upwards force, right, is vertical, whereas it is moving to the right. And since these two are perpendicular, they're at right angles, there is no work done. So have a look in the mark scheme for that other argument. Alright, let's move on. So during its descent back to the ground, it is traveling at a constant speed of 0.5 meters per second, and it malfunctioned at a height of 1 meter. So the motor stopped, that's a bit sad, and it fell to the ground. Right, so instead of having a controlled descent, it is now uncontrolled, and that it is just in free fall. And we're also told that it's already dropped off the crate, so it'll be a bit lighter. So in fact, I think it would only have a mass of 20 kgs. Alright, complete the energy transformation equation as it fell from 1 meter. So what type of energies does it start with? And then what type of energies does it end with? Right? Just as it hits the ground. So let's ask ourselves, does it start at some height above the ground? Yeah, it's 1 meter, so it definitely has some potential energy, EP. Does it start moving? Like, does it start with some speed? Yep, it is moving down, so it also has some initial kinetic energy, EK. Okay, now the motor's stopped and it falls or plummets to the ground. As it's falling, what's happening to its potential energy? It decreases, and so where does that go? It goes into more kinetic energy. So as it hits the ground, it'll be traveling faster than 0.5 meters per second. Okay, and what other energy does it transform into? So at ground level, there's no potential energy relative to the ground. So often in questions like this, we consider heat losses or heat and sound. So you can write heat/sound, right? And we call this the lost energy. It's the wasted energy. Yeah. And so this question is actually merit if you get all 4 correct, but achieved if you only get 3. Okay, so now part D is a calculation question. So calculate the final speed as it hits the ground. Well, we know it starts with potential and kinetic energy, which we can work out, and then that converts entirely into kinetic energy, and we will ignore, right, we will assume that there is no lost energy. In reality, there will be a bit, and in fact, jumping ahead, that's part E. So for our calculation, it is fair to assume no heat lost, yeah, but you may be expected to justify why you assumed that. So let's calculate this one. It says, gives us a hint, find its kinetic and potential energy at 1 meter. So let's do what it says. Kinetic energy is equal to half times the mass times the speed squared, right? It's the energy of motion, where the mass is no longer 50, right? Just reading the question, it's changed to 20, so it's dropped off the 30 kg crate. The speed is 0.5, and don't forget to square it. Very easy mistake, happens all the time, don't let it be you. And if you punch that in on your calculator, you should get 2.5 joules. All right. Now let's find the potential energy. Mass times gravity times height. Mass we know, 20 kgs. G, again, assuming on Earth, it is 10. H, what's the height? It's not 20 meters anymore. It is now 1 meter. 20 times 10 is 200. 200 times 1 is still 200 joules. Okay, so looking back at our energy transformation equation, we've worked out the starting energy. So in fact, let's add those together to give 202.5 joules. That is how much energy the drone starts with. Right, mechanical energy. Now, that converts to kinetic energy. So I'm going to write kinetic energy out again, equals half mv squared, but this time, instead of solving for kinetic energy, we already know how much kinetic energy it will have, assuming no heat is lost. So we know EK is 202.5. We know the mass is 20, but we don't know the speed, right? V, and don't forget to square it. So now we have an equation, right? If you're confident in your maths, this is a quadratic equation because it's V squared, but this one's pretty easy to solve. So to solve it, we could do half times 20 to start, and that gives 10. Everything else stays the same. Now if we're solving for V, before we square root it, we need to get rid of the coefficient. So we need to divide both sides by 10. Because what's 10 divided by 10? Come on. What's 10 divided by 10? 1, right? Or just, it's 1. So that means we don't need to write the number at the front. And 202.5 divided by 10, well, we shift the decimal 1 to the left, so 20.25. And what's our last step? We're solving for speed, not speed squared, so we need to square root both sides. And I believe that's 4.5. Yep. 4.5 speed meters per second. Whew. And that is an excellent question. If you just got the kinetic energy and the potential energy, that's achieved. If you then added them together and started making progress towards the speed, that's a merit. And if you got the right final answer, that is an excellence point. Alright, and now let's go on to part E. State what assumption you made for the calculation, and why the actual final speed will be less than we predicted. So again, that's going on to this heat lost assumption. So we assumed there is no heat lost. That was our assumption. So let's state that. So I assumed no energy lost or transferred as heat. That was the assumption. And now, how does this assumption make it so the actual final speed will be something more like 4.2 meters per second instead of 4.5? So what does this mean? This means the actual final kinetic energy, remember that's the EK on the right hand side of this energy transformation, that kinetic energy, which we said was 202.5, will actually be less. So this means the actual final kinetic energy will be less. And if you want, you can put in the number, but you know, we're just comparing. So it'll be less. Now what does that mean in terms of speed? Well, looking at the kinetic energy equation, if kinetic energy decreases, speed is also going to decrease. So the final speed will be less. Full stop. Now, this isn't a perfect answer because we haven't mentioned friction anywhere. So I assumed no energy loss as heat. In other words, I ignored friction or air resistance. So that just makes our answer a little bit more well-rounded because we've talked about the force, friction. By ignoring it, there's no heat loss. But if there was heat loss, the final kinetic energy would be less, and so the final speed would also be less. And that is another excellence question if you got all of those points. Alright, so that's question 1 done. Take this time now to just, look over your answers, read your notes on mechanical energy before we move into the next question.